Easy enough, right?
Whoa.
But now imagine it's whizzing past you at, like, almost the speed of light.
Ah, yeah, then things get weird. Our everyday ideas about size just break down.
Exactly. And you sent over some fascinating material looking at just how a particle's size, and I'm putting that in air quotes here,
Hmm.
seems to change when it's moving incredibly fast.
That's the plan for this deep dive. We're drawing on special relativity, particle physics, all the good stuff.
So the mission is basically to unpack what your sources say happens, figure out what physicists even mean by size at this level,
Because it's not straightforward.
and see what happens when these tiny things hit that cosmic speed limit.
Right. It sounds completely counterintuitive, I know. Why should speed change perceived size?
Yeah.
But the physics, as your sources lay out, actually gives us a pretty clear, if mind-bending picture.
Okay, I'm ready. Where do we start?
Well, the main effect, the big one from special relativity, is something called Lorentz contraction. Sometimes people just call it length contraction.
Lorentz contraction. Okay. What does that mean for what we actually see or measure?
It means, from your viewpoint, you standing still, watching this particle zoom by any dimension of that particle that's lined up with its direction of motion appears shorter.
Shorter than if it were just sitting there.
Exactly. Shorter than its proper length, which is the length you'd measure if you were moving along with it or if it was at rest relative to you.
So if it's flying past me horizontally, its width gets squished.
Precisely. Squished is a good way to think about it. Your material gives the formula L equals L times the square root of 1 minus v squared over c squared.
Okay, well, let's break that down a bit.
Yeah, sure.
Yeah.
L is that rest length, the proper length. V is the particle's velocity. C is the speed of light, the constant. And L is the contracted length you observe.
Right. And that square root part, 1 VCC chi, that's the key bit.
That's the relativistic magic, yeah. It's actually related to 1 over the Lorentz factor, gamma, which pops up everywhere in relativity. It basically tells you how much space-time effects kick in.
And it all depends on how fast V is compared to C.
You got it. So think about what happens when Vald gets really, really close to C.
Okay, so VC gets super close to 1.
Right.
Which means 1 minus that gets super close to 0.
And the square root of something approaching 0 is?
Also approaching 0. So L, the length I see, heads towards 0.
That's what the math predicts and what your sources emphasize. From your stationary perspective, the particle appears to shrink, getting flatter and flatter along its direction of motion.
It looks like it's becoming infinitesimally thin.
Potentially, yeah. As V gets arbitrarily close to C, L gets arbitrarily close to 0, like a tiny speck getting pancaked.
Wow. Okay, but you said along its direction of motion. Does that mean only in that one direction?
Yes. Crucial point, and your sources are clear on this. Lorentz contraction only affects dimensions parallel to the velocity vector.
So dimensions perpendicular, like its height or depth, if it's moving left to right, they stay the same.
Completely unaffected. No change at all in those directions.
Okay, so let's ditch the particle for a sec. Imagine something simple, like a perfect little ball bearing.
Right, like in your source material. If you saw that perfect sphere whizzing past at near light speed.
I wouldn't see a sphere.
Nope. You'd see something squashed. It would look like an ellipsoid, flattened along the direction it's moving, because only that dimension contracts. Sideways, it's still got its original diameter.
This is where my brain starts to ache a little, this flattening.
Yeah.
It's not like the particle is actually getting physically squeezed, is it?
Excellent question. No, it's not a physical deformation. Your sources stress this. It's an apparent effect.
Apparent to me, the observer.
Exactly. It depends entirely on your frame of reference and your relative motion to the particle. If, hypothetically, you could ride alongside the particle.
Which I can't, but okay.
Right. But if you could, you'd measure its normal, proper length, LU. The contraction is purely a result of how space and time coordinates transform between different inertial frames. It's about perspective.
So it's not getting bigger, which might be a naive guess about going faster.
Definitely not bigger.
It's actually appearing smaller, flatter in that one direction.
Correct. Your sources explicitly say there's no maximum size it achieves. Instead, the trend is towards a minimum apparent size 0 in the direction of motion from the stationary view.
Okay. Increasingly flattened. Got it.
Yeah.
But this whole discussion hinges on the idea of size. What does that even mean for a fundamental particle? Like an electron, it's not like measuring a football.
That's a huge point. And yeah, your sources dive into this complexity. For truly fundamental particles, electrons, quarks, the ones in the standard model, we often treat them as point particles.
Point particles, meaning zero size, no volume.
In the standard model, yes, they're treated as having no intrinsic spatial extent, 0 dimensions, essentially.
Okay. Then, if they have no size to start with, what exactly is Lorentz contracting?
Right, it seems paradoxical. In that case, it's not shrinking some pre-existing physical dimension. It's more about how the particle's presence or its interaction potential is distributed or localized in space-time from your perspective. It affects the observable spatial characteristics, how you'd map its position over time rather than shrinking a physical thing.
Okay. But not all particles are fundamental points, right?
Hmm.
What about protons, neutrons?
Good distinction. Composite particles. They are made of other things, quarks and gluons bound together. And they do have a measurable finite size. We talk about things like their charge radius.
Okay, so that kind of size.
That kind of measurable physical size, your sources confirm, is subject to Lorentz contraction. A proton moving near light speed would indeed appear flattened to a stationary observer. Its measurable radius would shrink along the direction of motion.
So for a proton, actual squishing from my perspective. For an electron, it's more about how its point-like nature appears spread or localized in spacetime.
That's a pretty good way to put it, yeah. It's a subtle but important difference based on the nature of the particle itself.
And then there's the whole quantum weirdness layer.
Oh yeah, wave-particle duality. Can't forget that.
Particles acting like waves. Your sources mentioned the de Broglie wavelength.
They did. Remember, quantum mechanics tells us particles have wave-like properties described by this wavelength, lambda. And the formula is simple, hhp.
H is Planck's constant, P is momentum.
Momentum, exactly. Now, what happens to momentum when you approach the speed of light?
It gets really, really big because mass increases, or effective mass.
Well, let's talk energy and momentum. Relativistic momentum is P equals E of V, that gamma factor, the Lorentz factor, 1 over the square root.
The one that goes towards infinity as V approaches C.
That's the one. So as V gets close to C, gamma shoots up towards infinity, and so does the momentum P.
Okay, momentum gets huge, and wavelength is H divided by P.
So if P is in the denominator and gets huge, O must get
Incredibly tiny. Really, really short wavelength.
Exactly. The de Broglie wavelength becomes extremely short for highly relativistic particles.
Does that mean the particle is physically smaller? Is that another kind of shrinking?
Not quite in the same way as Lorentz contraction, making it look physically flatter. Your sources clarify this. A very short de Broglie wavelength doesn't describe its physical dimensions like a radius.
Okay, so what does it mean then?
It describes its quantum wave nature. A shorter wavelength means it oscillates more rapidly in space. Crucially, it means the particle can interact with things on a smaller scale, or probe finer details. Think of it like having higher resolution in the quantum world.
So shorter wavelength equals ability to see smaller stuff, not necessarily being smaller stuff physically.
That's the idea. It relates more to its interaction scale and quantum behavior.
Okay. There was one more piece in your sources.
Yeah.
About energy, right? Not size, but related.
Absolutely vital, because while that one dimension might look like it's shrinking, something else is growing without bound, the particle's total energy.
EMCC, but with the relativistic factor.
Precisely. Total energy E is a fishbowl. And just like with momentum, as E approaches C, that gamma factor heads towards infinity.
Meaning the energy required also heads towards infinity.
Exactly. An infinite amount of energy would be needed to actually reach the speed of light for any particle with rest mass.
Which isn't possible.
Which isn't possible. That's the fundamental reason massive particles can only approach C and never attain it. The energy cost becomes infinitely high.
Wow. Okay. Let's try and synthesize this whole picture from the sources. If I'm standing here watching a particle zip by near light speed, what I perceive is that its length in the direction it's moving is drastically shrunk, maybe looking almost flat because of Lorentz contraction.
Right, trending towards 0 thickness in that one dimension.
But its dimensions perpendicular to that motion, like its height, are totally unchanged.
Correct. Looks squashed, not uniformly shrunk.
And this isn't something the particle feels. It's purely an effect of my observation relative to its high speed. Someone riding along wouldn't see it.
Couldn't have said it better myself. It's observer dependent.
Plus, the very idea of size is complicated. If it's a fundamental point particle like an electron,
then the contraction affects its apparent localization or spatial properties in space-time, not a physical radius.
But if it's a composite particle, like a proton, with a measurable radius,
then that radius does appear contracted in the direction of motion.
And on top of that, its quantum waviness, its de Broglie wavelength, gets super short.
meaning it can interact with things on a much finer scale, probing tiny distances.
All while its energy is skyrocketing towards infinity, which is why it can't ever actually hit light speed.
That sums it up pretty well.
So the takeaway isn't that particles reach some maximum size at high speeds, but rather, from our stationary view, they appear increasingly dramatically flattened along their path.
Exactly. Flattened, not bigger. It's a beautiful, if strange, consequence of how space, time, and matter behave at relativistic velocities.
So the key point from your sources really hammers home. Stand still and watch something fly past near light speed, and you'll see it dramatically contracted, looking almost squashed to zero thickness, but only in the direction it's traveling. Other dimensions. Totally normal.
And it really forces you to confront how tricky and context-dependent the concept of size is, especially when you mix quantum ideas with relativity.
Definitely. Which leads to a final thought, maybe something for you listening to chew on. We have fundamental particles, like quarks, treated as points with no size, and then composite particles like protons with a real radius that does contract. How might these fundamentally different ways of thinking about size change how we actually picture or even model matter when it's pushed to these extreme near-light speeds?
Yeah, how do those two pictures coexist in our models at the edge of physics? Something to ponder.